All right. So we're all connected there. That seems to work nicely. I'm going to test connecting to the room code. I'm joining from here. I think she said this computer. This computer to set up to the Zoom?
Oh, I'm gonna set it up for here.
So if you have
Oh my
meeting
gosh,
ID.
look at that.
Yeah. My
It's
gosh.
fun when it works.
That's really fancy.
We need the ID and the password.
Aye, aye. Okay. Oh gosh. There we go. Nope. So it says I'm. Oh. One second.
Turn on our audio, and that we should be able to hear through there.
Perfect.
And then, do you allow like participants to ask questions at the end, or
We do, yeah.
Okay, so then they should come through that audio when it is time for questions. So they'll hear us. You won't feel like you're talking through a microphone right now, but they should be able to hear us.
Okay.
When they speak through the computer, that's the speaker you'll hear them through.
Wonderful. And we'll test that once we get someone in the room there.
Yeah, or even I could join it.
Oh,
and
how
go
about
like
you?
in the
Yeah,
other
yeah.
room down the hall,
Let's test that.
Okay, let me just get the meeting number and then.
So the meeting number is 933-3279-0309.
I'm gonna stay here for a second. You can admit everyone too. Okay, so here's what you're seeing.
Oh, see that.
And then now that you've joined, you can share your screen.
Okay.
I think you might read. Someone to go.
And then do you go by William or Bill?
No.
Bill. Okay.
Okay. I just always say advance a slide, see how that looks.
Let me check.
That seems to be working. I'm gonna stay online.
Awesome.
Don't end it just yet. I'm gonna listen. So just have a look.
And then either Caitlin or I will introduce you at the front.
Okay.
We usually ask people to hold off on their questions until the very end because
Okay.
we've got some very, very eager folks.
Okay.
But the crowd's really nice tonight.
Okay, awesome. Maybe
We're smaller companies.
Hello.
Hello.
Hey, I can hear you. Can you hear me?
Fantastic. I can hear you just fine.
Awesome. Okay, and I can see the trading room. William, you're gonna want to turn off your camera. I don't think you'll need your camera. And then we can zoom in just a little bit too on the front screen there. So we can see you a little bit closer up, but I think we're good.
Awesome. Yeah.
Thank you. Be right back.
Fantastic. Thank you. Yeah, this is neat stuff.
I hope so. Hope it's of interest. How long do you have to lather on up here?
So we get kicked out at, oh gosh. They are pretty strict about on the hour at 8.
Okay, so I'll go in at 7.
Yeah,
Okay, and we
We'll
need
start
time
at
for
7.
questions. So like 40 minutes.
about 40 minutes.
Okay.
Yeah. then everyone kind of clears out pretty fast, but you should go and enjoy the food and the
Okay.
drink and the networking.
Okay, I'll do that. So stand here, talk, and I can
Yeah, you're
click
totally
through
welcome to
and-
stand there. I'm gonna try and zoom in on you just a little.
Okay.
I think I need to actually do it from the Zoom, but that's fine.
This is,
And I can see that through here, so you don't need to be in the room if you wanna go.
Okay, all right.
Something to eat.
Sure thing. Super, thanks for the help. That was too easy.
Please,
Wow.
let's not jinx it, knock on. That's the thing, are you gonna keep it up and then just,
I'm gonna keep it up and then I'll go
Okay.
and use this for registering.
I'm gonna mute this room until you guys are ready.
Fantastic.
These people come in.
Oh, yeah, let me grab my cord here.
Okay, everybody, we're gonna get started. Thank you guys for coming tonight. I just want to go with a few announcements before I introduce the talk. So our next talk will be May 21st at Optica, so it'll be the last talk of the year. And we will have, what's her name again?
Susanna, I'm drawing a blank on her last name.
Susanna Marcos.
Yeah.
Susanna Marcos. She is the head of the Visual Center at
The
Rochester.
Center for Visual Sciences.
Visual Sciences, thank you. And so her talk will be optical technologies for improving eye care. It will go over adaptive optics and high resolution imaging. Recently, some of the technologies have made their way into the optics laboratory. It will address technologies such as wavefront sensing, visual simulators, fully quantitative optical coherence tomography, and elastography, and new correction alternatives that they have inspired.
And the abstract and her bio are on the website.
Yep, everything's on the website. And that'll be the last talk of the year. There's also a few more outreach events if you want to get in front of kids, explain optics to them. We have those listed on the website as well. Audrey is the chair of those events, so feel free to speak to her to learn more about those opportunities. Our talk tonight is recent progress in small satellite constellations for passive microwave atmospheric sensing. Our speaker is William J. Blackwell. He received his BEE degree in electrical engineering from Georgia Tech and the SM and SCD degrees in electrical engineering and computer science from MIT, where he was a National Science Foundation Graduate Research Fellow. He's currently a laboratory fellow with the Applied Science Systems Group at MIT Lincoln Laboratory, where he leads a number of projects involving atmospheric remote sensing, including the development and calibration of airborne and spaceborne microwave sensors, the retrieval of geophysical products for remote radiance measurements, and the application of electromagnetic signal processing and estimation theory. He's the principal investigator of the NASA TROPICS Earth Venture mission and was previously the NPOESS Integrated Program Office Sensor Scientist for the Advanced Technology Microwave Sounder on the Tuolumne National Polar Partnership Satellite, launched by the National Oceanic and Atmospheric Administration. He has co-authored the books Neural Networks in Atmospheric Remote Sensing and Microwave Radar and Radiometric Remote Sensing, and has authored more than 200 additional publications related to atmospheric remote sensing. He is a IEEE Fellow and an AIAA Associate Fellow. Please give it up for William Blackwell.
It's a pleasure to be here. I'm going to be talking about atmospheric remote sensing. And, the wavelengths that you're going to hear about tonight are a little longer than you're used to hearing about. So I'm going to talk about passive microwave sensors. And the idea here is to use the microwave wavelengths because from a spaceborne perspective, they can penetrate the cloud tops and reveal really nice imagery of weather phenomena. So in the middle here are images of tropical cyclones taken at 205 gigahertz by the 5 tropics satellite constellation members. And you can see, all kinds of nice features of the hurricane eye and the rain bands. There's very cold scattering that we can see, convective cores, really nice imagery. And the evolution that I'm going to talk about is new ways to get these measurements. We've been making measurements like this from space for decades with big, expensive satellites. The IMPO satellite that was mentioned was many billions of dollars. And the idea was, can we, shrink that satellite down? This is the size of a loaf of bread, right? So it's a 10-pound satellite and largely make the same kinds of measurements, make those satellites relatively affordable, proliferated constellation, and get a lot of imagery like this. So I'll talk mostly about the TROPICS mission and how this is changing how we're making weather measurements around the world. And at the end, time permitting, I'm going to talk about a different kind of microwave sensor, which is using a reflector rate. So I point out that these are really tiny satellites. And one regret of that is that the antenna size is pretty tiny, which means I need to use millimeter wave channels for useful resolution, spatial resolution. I want to use lower frequency channels that can penetrate even more into the storm and reveal more about the rain underneath the clouds. And for that, I need a bigger antenna. So this is a factor of 100,000 bigger in area of the aperture. And this is a reflector array that folds out from a small satellite. So it's still relatively small, it's deployable, and the reflector array steers the beams around. So I'll walk you through the story of the instrumentation, the science that we can do with these new measurements, and talk about some technology for the next generation of these systems. So a little bit of motivation. And by the way, so I'm okay with the Zoom guys online. They're cool. They can hear me and everything's good there before I get too far. No complaints on audio or anything. We're good. Awesome. Okay. So a little bit of motivation. So so severe and extreme weather, extremely consequential, right? So I'm showing you here, over time, the kind of the cost of all natural disasters, right? And it's large, many billions of dollars. And most of that is tropical cyclones, right? So there's a tremendous motivation to do a better job predicting those, where they're going to make landfall, what the intensity will be, so we can improve our disaster management, right? So it's very huge consequence. We're trying to get the forecasting better, the track of the hurricane and the intensity. Those are the two things that the forecasters are really interested in improving. And there's a big payoff if we can do that. Okay, just to illustrate that. So one of the poster child for, a whiff on the forecast for hurricane was Hurricane Irma. All right, so 2:00 on a Thursday, this was, 5 years ago or so, all the models were showing, okay, it's going off the eastern coast of Florida. Let's get all those people evacuated, move them out. And then just a short time later, 32 hours, it completely changed course, right? So now it's going over the western side of Florida. Just kidding to the guys over here. Now you guys need to move out, right? So that's chaotic, and it causes all kinds of problems for people ignoring the forecast. So we got to do a better job of understanding where the storm is going to go, when it will get there, so we can do a better job of all this emergency management, for example. So the way we do that and is forecasting, and the way we do the forecasting is driven largely by all kinds of observations. And so this is a very cartoony, not to scale kind of slide, right? So I've got geostationary satellites that are actually flying lower than the polar satellites. Just ignore that for the moment, but all kinds of things are feeding the forecast models, from satellites in polar orbit, 800 kilometers up, geostationary satellites, 40,000 kilometers up, aircraft, weather balloons, ground-based radar, shipborne things, buoys drifting along. All this goes into the forecast model. And you can ask,
Can you, I think, let him speak so he can get to the.
I'm happy to do it either way if it's a quick. Just go keep going.
Yeah.
Hold that
You're
thought.
not going to get to.
Hold that thought. Okay. So one interesting question is, what's the relative importance of all these thousands of things that are going into the forecast model? What's giving us the biggest benefit of the forecast? And you might be able to guess what that is. So here's all kinds of acronyms. I apologize, I'll walk you through this. So what I'm showing you here is the relative benefit of all the sensors essentially on the page and how much they contribute to the forecast. And at the top, the most impactful measurement is something called the Advanced Technology Microwave Sounder. Number one, right? And then we have the weather balloons, geostationary wind, which derive from water vapor, another microwave sensor, aircraft data, infrared things, radial occultation, buoys, scatterometers. But at the top is the microwave sounder, right? So we're motivated to, make improvements to the microwave sounder, fly more of them, improve our revisit. One of the regrets that, these satellites are big and expensive, take decades to design and build and deploy, is we don't have very many of them. Right? We only have a couple of the microwave sounders. We need more of them to improve our revisit. Those are very valuable. Okay, so just to level set you on kind of the current state of the art as of 5 years or today for NOAA. So here's a picture of the Advanced Technology Microwave Sounder. So this rotates. So as the satellite's flying along, these reflectors are rotating, steering a beam across the Earth to make an image. So this thing is about the size of a washing machine. and it flies on the satellite here. The INPOs, what used to be called INPOs, and there's a person leaning over the bench for scale. So it's a really big satellite. The life cycle cost of that was many tens of billions of dollars. They're exquisitely good instrumentation, right? So this is a fantastic suite of instruments that does all kinds of things. But here's the microwave sounder. And looking at this, one thing that's somewhat apparent is that most of this, right, you have to have the antenna to get the spatial resolution. But a lot of this electronics, you can ask the question, can we miniaturize that? Make it smaller, more affordable, leverage kind of commercial parts like what's in this iPhone, right? From RF amplifiers and data processing, and use that for this electronics, which is kind of component-based, block to block to block, all wired together. So that's one kind of technology question is, can we make this smaller, more affordable, and proliferate a constellation and fly a lot more of the most valuable type of items that we have? Okay, so on that thought, this is where my work comes in. So about 15 years ago, we started to ask the question, what would it take to start to miniaturize that microwave sounder so we can fly it on a really tiny commodity class satellite? It's much cheaper to launch and operate and so forth. So we started to look at the core technologies, the receiver. So right down the road at UMass Amherst, we were talking earlier on the pizza about radio astronomy and astronomy in general, but those guys make the best instrumentation for what we wanted to do. This array was perfect. So they helped us to build the receiver that we needed. And then we started to kind of bootstrap off of that. So we built a series of prototype satellites. These are all what we call 3U CubeSats, this kind of 3 to 5 kilogram class satellite with spinning payloads. We started to fly those through internal funding, collaboration with MIT Air Astro Department. And we started to convince ourselves this is actually viable, right? We can make these receivers and make the measurements and fit them on a spacecraft. And with Micromass 2A back in, this is 2018, we did that for the first time and showed that it was a viable measurement. So that was a big deal. And then we were off to the races. So then we won the NASA Tropics Constellation mission. We put in a proposal and were selected for that. So we built 7 of these 3U CubeSats for Tropics. We flew 5 of them. We'll talk about what happened to the other 2 coming up. But these are really capable, very tiny spacecraft with a rotating payload, a solar array that moves to track the sun. The bus is rolling to allow the antenna to talk to the ground and the array to put on the sun. And all that's going on, we have to geolocate the radiometer and know where we're pointed to exquisite accuracy. So it's a lot going on. It's a little tiny satellite. So I'll talk about that. So we launched the first one in 2021 and 4 more in 2023. And people started taking notice of that. So we did a tech transfer of that technology to a local company, Tomorrow.io. And they built a constellation based on Tropics, which now has 11 satellites. And they got, they're now getting 60-minute global revisit rate. So back to the ATMS and the what we call the GPSS satellite. We have a couple of those so that will fly over a point on the Earth and has to wait for the Earth to rotate underneath it. So the next time it comes around, 12 hours later, you get the same spot on the ground. So you're waiting 12 hours to revisit the same storm. We have a very small handful of those satellites. So we're waiting about, call it 6 hours for a visit. So a hurricane is dynamic, chaotic, lots changing in 6 hours. With Tropics, we're able to get down to 60-minute revisit instead of 6 hours. Now we're doing 60-minute over a latitude band near the tropics. And Tomorrow.io has done 60-minute globally, right? So we have a much improved revisit rate by flying a lot more of these satellites. And they've announced that they're going to do another generation called Deep Sky. So we're involved with that as well. So let me talk about the Tropics mission. And before I do that, just a few words on the observables and what we're trying to measure and how they relate to tropical cyclones. So these are fascinating for those of you who know anything about this stuff. So it's really a heat engine. There's moist air that's warm that drives the storm, forms all these circulation patterns. We get rain bands and eye forms, and the thing intensifies. So what we're trying to do is characterize the environment around the storm, the moisture in the storm, the eye, the warming in the eye, and the rain bands around the eye. Those are all things that we can measure with a microwave radiometer. That's the reason that microwave sounder is at the top of the forecast impact. Measure all those things and see below the cloud tops that obscure the infrared and the visible that we fly on geo and the polar satellites. So that's the game plan. So the idea behind Tropics is to fly a constellation of satellites where we're flying more frequently over the satellite, over the storms to give us more frequent revisits. So here is the payload, the instrument. So it's a very tiny instrument. And here you see, compare this to ATMS. So here's the aperture. It's 8.5 centimeters across, but the electronics are all tightly compacted around the cube, around the corners and the sides. Most of this block, 10 centimeters on an edge, is that 8.5 centimeter aperture, right? So you really aggressively compacted and integrated all those electronics. And there's a very small pancake motor that turns that to get the measurements that we need. So this is scanning at 30 RPM as it flies along. And we've got a fantastic science team, external partners from NASA, NOAA, MIT, Wisconsin, Miami, and others helping us process the mission data and get that out to the weather forecasters. So I'm the PI of the mission. Scott Brown and NASA Goddard are project scientists, and we're working with all these great scientists around the country on Tropics. Okay, so bringing this back to ATMS, just to give you a sense of how we stack up. So ATMS is this dish, laundry, washing machine size thing, dishwasher size thing, and here we are, Wonder Bread size, right? So it's like a factor of 100 in mass and power, cost, right? And we get, I've given you a hint already. The data that we get off of this is exquisitely good, even at a factor of 100 reduction in all these key parameters, right? So how do we do that? And how does it impact forecasts? So I'll give you kind of a technology story and a science story, how that's worked out. On the technology side, you ask the question, so how do you do that, right? So how do you take the washing machine and scrunch it into a coffee cup, right? And a lot of it is, integrated engineering, right? So there's the integration of components and parts, and at kind of the component level and at the system level. There are a lot of challenges with the structural making things, the antenna has to be aligned. There's a parabolic reflector back here that's fed by feed horns. You can't really see from this picture, but I'll maybe show that later. That all has to be aligned and survive launch, thermal deformations and distortions. So we can work that. A lot of integration in electrical and miniaturization in the electrical side. So there's all kinds, of commercial parts that we're flying now, where the JPSS, the big $10 billion satellite has, flight qualified, space qualified parts. We're not doing that exactly for these satellites. We're flying commercial parts, and then we're radiation testing them to make sure that they'll work okay in space, which is not mandating a space qualified part. We're doing some testing to convince ourselves that it would be appropriate. Fancy mechanisms for spinning this in a very kind of high aspect ratio flat package to do that. A lot of state-of-the-art fabrication to build all this and to test it, and then it all comes together. There's it's hard pressed to put like a thimble of water into this thing and have it not full. This is so packed full of electronics and parts, and we're using CAD to make that happen. Even the routing of the cables and the waveguides and the antennas are tucked in a corner, pointing at the reflectors. There's a lot of fancy engineering to make all that happen. Okay, so we built 7 of these. I think we put these, we finished them and had our kind of acceptance review with NASA the week before COVID started, which was kind of, I guess it could have been worse, right? And then NASA went out and looked for a launch. And again, this is a burgeoning kind of small satellite commercial space launch market. There weren't a whole lot of options back then, right? So SpaceX was one option, but that was $60 million. You want to pay $60 million to launch a $1.5 million satellite. So the companies were places like Astra and Rocket Lab. So we went up, we built 7. We built a qualification unit. We launched that one quickly just to make sure, we're waiting for the launch to happen. Let's fling that thing up and see how well it works. It worked fantastically well. We got great data out of the qualification unit. While we're waiting on that one, NASA went out for their launch procurement. We were on Astra. The two satellites went up on Astra, got almost to the top, and they ran out of fuel. So for reasons, technical reasons. So that was a bummer. So we lost 2 satellites. But one of the nice things about the mission is that we built in the design, robustness to failure. So we could satisfy our mission requirements with only 4. But we said, NASA, these have got to work. The launches have got to work. Please get us up there. And they did. So Rocket Lab, we launched out of New Zealand in May of 2023, 2 for 2. So we got 4 satellites up there. One interesting thing about this, I'll talk about this more, is the inclination, like where in the orbital planes are they? So the NOAA satellites are sun synchronous polar orbits at 97 degrees. So they're flying over the poles. We're not flying over the poles. And the reason we're not flying over the poles is there are no hurricanes at the poles, right? So we're flying over the regions where the hurricanes are most likely to form. That inclination is not a polar, but it's like a 32 degrees, right? So we're flying over the latitude band where the hurricanes are. Okay, so we launched the Pathfinder into a sun synchronous orbit on a SpaceX rideshare launch 2021, and the 4 Constellation vehicles in May of 2023 out of New Zealand, by the way. Beautiful launch site. Okay, so here's a picture of the satellite right before it's going to be launched, with the payload spinning and the array turning, give you a sense of that. And then here's the ground track, the swath of the satellites as they're flying. So it's a 2,000 kilometer wide swath from an altitude of 550 kilometers. You can see the inclination angles with respect to the equator here. So they're not going over the poles, they're going, just the middle third of the Earth, if you will, mapping out a swath as they go. Okay, so here's kind of the global view of that animation I just showed you, showing the swath coverage, inclination. And one interesting thing about the Tropics mission, so this was a cost-capped mission by NASA, which means that if you go outside your cost cap, or if you even project to go out of your cost cap, they cancel you. So there's a lot of pressure to maintain the cost and schedule on the mission. And we leaned in really hard to the commercial space sector for our launch, as you saw before. That was one of the artifacts of that. Ground stations, we can go out and buy time on commercial ground stations. Now we don't need to use the NASA Deep Space Network or the Near Earth Network. We can go to commercial, almost commodity class, parts for CubeSat buses, mission operations, and then rely on all the people that have done this before for the big NOAA systems for the data calibration, processing, exploitation, and forecasting at Lincoln, Wisconsin, and NASA to get the data out. So one interesting thing about this mission is this is a research mission. So we didn't have any requirements for data latency. Like we take a measurement. The forecasters want that data instantly, right? In an operational context, but this is a research mission. So we were able to get additional funding to add more ground stations so we can get data latency with about 60 minutes, which is fantastic. So we can get the data down to the forecasters they can actually use. I'll talk more about that later. That was really important. I'll show you why. Okay, so the real payoff for Tropics is this temporal revisit rate. We're putting up a lot more satellites in this specialized latitude bands. We have a lot more observations of a tropical cyclone. So what I'm showing you here is time is running across the screen. We have geostationary looks at the tropical cyclone very frequently. But we only get the cloud tops. Okay, the infrared and the visible can't penetrate with the clouds. We've got the polar orbiting satellites, but there aren't very many of those, right? So there are big gaps in between this guy will fly over, you got to wait for the next guy to fly over. Tropics fills in the temporal gaps, right? So you can see, the eye forming, the eye wall's closing up. They're starting to get strengthening. So the eye wall is starting to become more well-formed, a pinhole eye, all these things you can see with this temporal evolution that Tropics provides. So that's really the payoff of Tropics is this temporal revisit that we haven't been able to get before.
What do the codes and labels mean?
Codes on the labels. Okay, so here, yeah, so
On the
this,
top of each image.
okay, so we have day, so it's September 7th, 6 Zulu time. So this is time. So this is 4 hours later, 2 hours later, 6 hours later, and so forth, right? So it's just time. Where here is, basically 2 hour snaps. And these are the satellites in the constellation. Pathfinder is 1356653 in the constellation. So we can fill in those temporal gaps. By the way, this is new data at 205. This is the new channel that we haven't flown before on the NOAA satellites. I mean, this is really cool data. You can see that eye very clearly. Resolve the eye. See the blue in the middle of the eye is interesting. I'll come back to that, how we use that. Okay, no, just a few words on the measurements that the CubeSats make. So again, we're rotating, we're kind of painting a swath of 2,000 kilometers wide. The measurements themselves have resolution of about, depending on the channel, 15 kilometers to 25 kilometers. So, you know, that's not exquisitely fine resolution, but it's fine enough to resolve the eye, right? So that's what's driving that. So that was really the whole driving requirement for this is, can you make this antenna big enough, fit it on the satellite, and get this resolution fine enough so you can resolve the eye? And the answer is yes, it works perfectly for that, right? So that story hangs together. And there's some details in here about the radios that we use and the avionics and the channel bandwidth. So I'm going to come back to this. So this has 12 channels between 92 and 205. We use some of those for temperature sounding and some of those for water vapor sounding. I'll explain what that is. Just a second. Okay, so more details on the channels. So 12 channels, there's an imaging channel at near 90 and near 205. And then there are 7 channels for temperature profiling. So we can derive the temperature in and around the storm as a function of altitude. So it's like a weather balloon, right? The weather balloon goes up and measures temperature as a function of altitude. We can do that with a sensor by using the spectral properties of the atmosphere for temperature and for water vapor. We get a water vapor profile using a line at 183 gigahertz. Okay, so how can we do that sounding? That's pretty neat. How can you use the spectral property of the atmosphere to give you temperature or water vapor as a function of altitude? And the magic there is Mother Nature, right? So there are these absorption lines. In this particular case, at 118.75, there's an oxygen line, okay? And what we can do is we can measure, listen to that radiance that's emanating from the atmosphere at channels that are really near the line and progressively away from the line. And what this does for you is, from a satellite in space, if I use a channel near the line center, there's a lot of opacity in the atmosphere, so I'm sensitive to the top of the atmosphere, right? And as I tune the dial and look at the channels off the line, I progressively penetrate more into the atmosphere, so I can measure channels lower to the ground, right? So as I move off the line, I'm measuring lower to the ground. And the way that happens is there's various radiance components that reach the satellite. Either there's the cosmic background reflects off a reflective ocean surface or a cloud. The atmosphere can go directly to the sensor. The surface will go to the sensor. It can reflect. So we can, the equations of radiative transfer allow us to disentangle these various components, use this relationship, and build up a vertical profile of temperature or water vapor. So this is the principle for sounding. We use that for temperature and water vapor. Okay. Okay. So that's the sounding part. There's also the imagery part, right? So this is taking a pretty picture of the storm. So back to our friend the ATMS on the JPSS satellite, and this is the best channel on ATMS for sensing or imaging a tropical cyclone. It does a nice job. Okay, pretty good. But look at us. Okay, this is tropics, and I've blown it up by a factor of 50, so you can see it on the view graph or the screen, right? Much better imagery, right? We got a much clearer depiction of the eye, the rain bands, all the scattering in the rain bands. So it's really nice imagery at this 205 gigahertz channel from tropics. So that's pretty cool. So again, we can see things here that we can't see with the state of the art. Much bigger imagery. Okay. So another depiction of how great the data is, even though that thing is so tiny and relatively inexpensive. What I'm showing you here is that 90 gigahertz channel, channel 1 from the Pathfinder. For the whole mission, just played, I'm speeding it up, right? So this is all the data from the WBN Pathfinder channel. And if you look carefully and know where to look, you can see tropical cyclones spinning up and moving along in both the Atlantic Basin and over here. Just really nice depictions of the water vapor moving over the ocean surface, which is really nice data coming out of these really tiny, relatively inexpensive CubeSats. It's amazing to me how great this data is. So we have this from all 5 satellites. Okay, now back to the central, the question is, okay, great. How does the tropics data help with the forecasting? Back to my chart with all of the lines on it. So here, ATMS, okay, and this is the degree to which the forecast is improved by adding the measurement. And with the tropics constellation, and this is a little bit unfair because there are 4 tropic satellites here and there are only 2 ATMS sensors. Okay, but remember, it's a factor of 100 in cost, so I'll take that trade. We're just better than they are for this over the tropics, right? So this is pretty phenomenal, right? That we're able to improve better than anybody else. So now we're the winner of the top, which is amazing. Now back to our example with the Florida, the East Coast versus the West Coast. Okay, great, but how about the track? So we have all kinds of examples. This is one of many examples showing that the track forecast is improved as well. So the black line here is the true track of a hurricane. In this case, I believe this is Franklin from 2023. And then the forecast without tropics in blue and green, the difference is like the lead time of the forecast, right? So it's not super great, right? The blue and the green are departing from the black by quite a bit. If we add the tropics data in, we get a much closer match to the blue and the black are almost on top of each other. So that's good. Just one case, right? So we looked at a lot of cases and we see similar things. This is the Goddard group that did this at the Global Modeling Simulation Office. We have other investigators that have looked also at looking at tropics data. So again, here's the black, the true. These are all retrospective cases. We can add the tropics data and see what it would have done. We start with the blue with no tropics data. We added in the temperature and the green, water vapor, and orange, and both the red lies almost exactly on top of it. We're pretty close to the black. So that's good news. The track forecast is improving quite a bit of tropics. So that's good news. Okay. And just for a complete picture, just to give you a sense of the products that we deliver for tropics, you can go to the NASA disk site and download all the radiance products. We've got the temperature profile product, moisture profile, rain rate, and tropical cyclone intensity. You go and download all that data if you want to. This is what the science team is producing. This is imagery, just to give you a sense for all the 12 channels, right? So imaging channel. And then these are giving you slices vertically in the atmosphere of temperature, water vapor, and more imagery. So really nice data there. We spent a lot of time on the calibration and stability, convincing ourselves that the calibration was stable. So this looks really good. We had to do calibration a completely different way on that very tiny satellite. That worked out very nicely for us. And we compare with all kinds of numerical models, reanalyses, weather balloons, to make sure that the observations that we take are actually faithful to reality, and they are. So the departures are close to 0 and very nicely Gaussian shape as you want them to be. And the linearity is good as well. So we look at the departures, again, comparing to a reanalysis over many observations, and that looks great. So just a kind of a snapshot of what we call calibration validation of all the data to make sure that it actually is, like I said, faithful to reality. Okay, and just a couple of, I can't resist, but put in a couple more images of just the storm evolution flashing through a couple of overpasses showing this eye closing up, right? So here it's partially formed, and then the next shot, what's closed up. So we know it's intensifying. The rain bands are getting really strong, these really cold temperatures, because it's scattering, the ice and the rain bands are scattering quite a bit. We'll keep looking forward. Now it's a really raging storm with this big eye, which we can very clearly resolve. But the hardest one is this one, right? When it's just starting to form, the eyes are really tiny. We want to be able to resolve that eye. We can, so that's good. And then here it's raging again. So you can see the evolution of the rain, the spiral arms, and very clear. Can you see the blue peeking through that eye? It's super clear. Very intense storm. Okay. Now, another cool thing, I mentioned this briefly earlier, is in the middle of the eye, there's something called a warm core anomaly. So this is a cut through a storm, showing you the temperature. This is relative temperature. This is temperature relative to an outside location. So it's really warm in this eye, and very moist in the eye, right? So we can measure this. Again, we can resolve this and measure what we call the warm core anomaly, which is very highly correlated to the intensity. So we can use that signature to try to estimate the intensity of the storm. And so our science team folks at Wisconsin have an algorithm to do that. And they estimate, so the true value is the black, our estimate is the dashed gray, and we can pretty much nail that intensity using that phenomenon of observing that warm core anomaly in the eye and correlating that to intensities. It's a very nice measurement that we can make. And back again to the latency that I talked about. So one of the maybe the most satisfying takeaway from the Tropics mission is it was a research mission for NASA, and the operational community embraced the data for real-time operational forecasting, which is unheard of for a research mission to do that so quickly. It's very, very uncommon. So we provided data from Tropics to the Naval Research Laboratory, the Hurricane Center, Joint Typhoon Warning Center, all over the world, and they're using this they were using it. It was active with all its forecasts. So the Tropics satellites deorbited at the end of last year. So the mission is over, but we're still doing all kinds of analysis on the science. This was a whopper storm. This is Conray. And this thing had a warm core anomaly of 13 Kelvin, which is just incredible. That's the biggest we've ever seen. Okay, so that concludes the Tropics picture part of the presentation. And I wanted to spend 5 minutes or so on what's next. What Tropics was successful, but what are the regrets of flying a really tiny satellite? What would you really like to have? And the regret of Tropics is that we don't have any channels that are lower than 90 gigahertz, and we want those channels. So we need a larger antenna. And larger antennas, the mass of the sensor scale, so like the third power of the antenna size, something like that. So we're looking at a new technology based on reflector arrays, where we deploy a panelized, fold-out reflector array that can electronically steer a beam in multiple wavelengths. So now we're down to 24, 31, and 50 to 58 gigahertz, which is the region below what Tropics can measure. These are even more sensitive to the rain and the storm. We can still fly this on a relatively small satellite and take advantage of rideshare launches on SpaceX. So just a quick summary on where the technology is on this. So just to point out, if I plot for you the ratio for current sensors, okay, remember here's our friend ATMS, here's Tropics. I'm showing you the ratio of the size of the aperture to the mass of the payload, mass of the instrument, right? I know for sensors we've been flying, it's kind of this progression. With Cruiser, because it's basically the whole sensor is an antenna, right? It's just a flat panel antenna. It's 2 orders of magnitude higher than anything we've ever flown before. If it works, we haven't flown it yet, but it looks good so far. And it's green. What does green mean? Green means these are all mechanically scanning. So you have to turn the reflector with a motor, which takes power and mass. This is electronically scanning. So I can point the beam anywhere I want at any time, look wherever, independently with 3 channels. So that's kind of a game changer for how I make these measurements. And there's all kinds of enablers that make this happen. And we're drafting on the coattails of the communications industry. There's more of this stuff too, like Starlink, right? Starlink is flying X-band phased arrays that cost, $50 to make. And that's the same kind of technology, silicon, which now is amenable to measurements at 50 gigahertz, right? So we can now start to use silicon-based processes that have low enough loss to use that for RF. So we're using that again. We're getting really good at deploying, precision structures. The metrology for, this is a 2-meter panel, right? So it's got to be flat. It's going to undergo a lot of thermal stress as this thing is going in and out of sunlight. hundreds of degrees Celsius that will deform the panel and degrade the beam. But we can use metrology techniques to let us measure that and correct for it. And now we can have a latency comp to the satellite to help us reconfigure on the fly what the sensor is measuring, how it's measuring, and make a better measurement. So all that stuff is possible. Okay, and that configurability is a really big deal, right? So that sensor is essentially software definable. I can point the beam at any place on the globe, or any place in the field of view of the satellite, I should say, at any resolution, right? So if we're overflying, this case is an atmospheric river off the coast of California, the action is in the red, right? So I want my finest resolution spatially on the red. I don't care what's going on out here, right? So I have a big broad beam. I can do all this kind of on the fly with a sensor to optimize the spatial. And there's analogous cases for spectral and even geometry, right? I can fly, if there's something I know a priori that's interesting, hurricane, I can look at it as I'm flying and continue to look at it even when I'm past it and looking behind me and do tomography, right? Those kinds of things. So all those are possible. And I just have a couple of slides on how this works. It's really amazing. So this reflector array has got two faces to it. There's a radiating side, essentially an array of patch antennas. And behind that is the magic of how we do the electronic beam shifting, steering. And that's essentially, it's a phase shifter. And the way that works, I think the best way to illustrate that is with just an animation. So the way that array is moving the beam around is it's imposing a phase shift on the surface at each frequency, right? So those phase shifters are making this flat panel look like a parabolic reflector. Okay, so it's shaping the beam and steering it around by virtue of this phase shifter. So there's all these RF integrated circuits that are doing that in real time behind the panel. There's on the order of 100,000 of them behind the panel. So there's a challenge of controlling them and managing, the connections and the thermal dissipation and so forth. So we have ways to do all that. I'm going to skip ahead just a little bit. Now, there's so many of those, the challenge of building this array is there's so many parts on there, right? So there are, hundreds of thousands of individual integrated circuits. So you have to be very careful of, even how you attach all the chips, right? These are ball grid arrays that have to be attached to a panel that's going to heat it up in the sun. It's going to cool down. So we have a sophisticated way to attach those. We test to make sure that all the connections have a high fidelity, that they're not going to fail on orbit. Turns out we don't need to have all of them work perfectly. We can actually tolerate 90% of them working and the array still functions quite well. So we did X-ray testing. We built up a surrogate, did some X-rays, and convinced ourselves that it's very achievable. So a lot of this is going on. We spent a lot of time trying to figure out how to bond the integrated circuits to the substrate with interposers, dealing with the thermal, the mechanical stress, and having it, you have to be able to build it, right, with a pick and place machine. So work through all that. So just to give you kind of a flavor of the challenges. On the thermal side, we have a sophisticated stack up, kind of a sandwiching of materials to help us move the heat away from the integrated circuits out to the backside of the array. This is a good shot of showing we have feed antennas here that are illuminated by the reflector ray. So the Earth is here, reflects off the reflector ray into the feed, into the radiometer. That's how it's measured. Okay, so there's all kinds of electronics to control all the beam shifters. Basically a big board of FPGAs to do all that over an SPI bus. And we've tested this. So we built a prototype first panel, tested that in the antenna range over at Lincoln Lab down the road. And the antenna patterns look really good. So again, this is working at 24 gigahertz, 31 gigahertz, and 50 to 58. And the patterns are spot on the measure versus simulated. So that's all great news. We're going to fly this on a balloon next year to convince ourselves that we can get that while it's on, up in the air, undergoing a lot of thermal stress. And these are the things that we care about. So we want to operate over all these frequency bands. We want to have very high quality antenna patterns. So we want most of the energy in the main lobe, no very low side lobe levels. And this is the big one. So this is the phase shifter losses. So this was, silicon processes, which are extremely cheap once you have the mask, are just about, they're not quite there yet, but they're really close to what we need. They will be there soon. So that's what's in the minutes. Okay. Just the last thing, this is my last slide, is you might be wondering, with a sensor that's that configurable, how do you test that in the lab, right? It can adjust its spatial coverage, look angle, resolution, spectral properties. And so basically what we've done is it's actually some optics here. So we've got a laser source, yay, okay, illuminating the backside of a metamaterial surface that has a very high emissivity in the microwave, right? So we're imposing a spatially resolvable scene on that what we call a scene generator that the radiometer can measure, and it can react to that, right? So it can calibrate it, estimate what this atmospheric model is putting into the scene generator, and react to it, reorient itself, change the spectral characteristics, spatial characteristics, where it's looking, the beam resolution, and so forth. And then we can compare that to the truth and see how we're doing. So we have a project with Colorado State to show that we can do this in the laboratory and prove and optimize all the reconfigurability of this sensor. Okay, so he was on time. So just a summary slide. So very proud of the Tropics mission in terms of providing new high revisit capabilities in the microwave for storm measurements, forecasting, much better revisit, even with the performance that we get with operational sounders. Sensors like Cruiser allow us to have larger apertures, lower frequencies, and their configurability allows us to do things like what I call cognitive sensing. The sensor is aware of what it's going to fly over, and it can reconfigure and optimize itself to make measurements of whatever that is. And with that, I'll stop. Make sure I have time for questions. So thanks very much for hanging with me.
So yeah, feel free to ask questions.
Do you want to ask yours? Good.
Anyone?
Yes.
This is one step past you in terms of your involvement, but these things generate reams and reams and reams and reams of data. Nobody sits at a screen looking at pictures as they come in. Can you at least give a little description of what happens to all this wonderful data?
Right. So I'll give you a little vignette. So in terms of the images and processing of the images, one of the most important thing of a hurricane is where the eye, what's the center of the eye? Where is that? Right. So that's something that we've been successful in somewhat automating, right? With AI type things that can figure out where's the center of the eye and how is it changing over time. Because that helps the forecast kind of level set the track, right? That kind of thing. So those kinds of tools, those are pretty basic, are coming along very quickly and getting really good, that kind of stuff. The next level is, I'll call those kind of, markers. Well, the next level is like the forecasting. Can you have an AI system help you with the forecast determination? There's a lot of active work on that, where they can try to, again, automate the process of looking at the imagery and all the data, making sense of it, where the humans can't. Like at the Hurricane Center, there's literally a room full of folks looking at the data, right, and writing reports, right? And that works well, but we can't. It's unsustainable for all this data, right? So I think that's really the thrust of your question, right? Is how we process all that.
Yeah.
Yes.
Do you do an analog to what the SAR people do with the active systems in order to synthesize antennas, or is that something you're already doing and I just quite understand it? Because you talked about the 14 kilometer or 15 kilometer spatial resolution,
yep.
And with these little CubeSats, couldn't you, with a coherent system that you can get?
So you could do that, and let me tell you a game changer on that one is these laser comm links, right? Now you can go out and buy almost, again, commodity, a laser terminal that's the size of a coffee cup. And that's what you need to coherently combine, those measurements. So that's a doable do. People are working on that. Yeah, it's interesting. Not yet, but it's coming.
Yeah, there's the buzzword in the weather forecasting industry of nowcasting.
Yeah.
How proliferated would these satellites have to be to truly get nowcasting? I know you talked a little bit about the 60-minute cycle time, but
Yep. Yeah, so I'm going to give you, one of my favorite answers is that depends, right? So, the nowcasting is a couple ways to look at the nowcasting. One is it's just kind of a simple extrapolation of the current state. You take the state, you extrapolate a little bit, and that's your nowcasting, right? So, and I'm oversimplifying. But so the error, you can drive the error down by doing exactly what you said, which is you add more constellation members and you bound and constrain that estimate even more. And the other thing, so that's happening. Your question is like, how much of that do you need before it can make a big difference? So, I'm going to come back to the tomorrow AO case, on the order of a dozen satellites, right? The 60-minute global revisit starts to get you part of the way there. So the nowcasting that's most useful for aviation, right? Where the pilots need to know, am I going to fly through a convective storm in 10 minutes? That's really hard, right? The cases that you care about the most are the hard ones. So I think we're ways away from having enough to do that. Maybe 50 satellites, 10-minute revisit for that kind of stuff. 60-minute revisit, I think, is better for less dynamic phenomenology, if you will, right? So I think the answer kind of is we're on the cusp of it now, but we need on the order of 5 times more to get really, no kidding, nowcasting that's aviation quality. That's my guess. I'm not really sure. Be thinking about it. Is that where you were going with that question? Okay. Yes.
So the size of your reflector array, why didn't you go bigger? What limits did you run into?
Yeah. That's awesome.
Why'd you unwrap the loaf of bread this way?
Yeah. So, okay. So the constraints on the reflector array were things like how many panels can you fit in an ESPA Grande satellite, right? So that's a definable volume, right? Because how much SpaceX will fly it and charge me $2 million or whatever. So there's that kind of thing, right? So that defines kind of a panel or a subpanel, if you will. The next thing is, okay, I need to deploy this thing, lock it into place. It's got to be sufficiently flat. Okay, sufficiently flat is lambda over 30 for my operating frequency, and that gets harder to do as my panel gets bigger. There's another constraint, right? So we kind of pick this happy medium, Goldilocks kind of panel thing. I can fit in the ESPA. I think I can solve the lambda over 30 issue, and that's kind of where we went. So if you want it bigger than that, then you have to be more aggressive with how stiff the panel is, and you can be more aggressive with your metrology, measuring it to exquisite levels. But we picked that because it's kind of a sweet spot. Yes.
Like primed mission and what advice do you have or lessons from the whole mission?
Oh wow! How long do you have? Okay, so there's a lot of interesting things about Tropics. So Tropics was a NASA. Do you speak the NASA-ese, the 5120.f stuff like that? A NASA science mission directorate flight mission requires all kinds of documentation that would fill this room up. And here we are. Tropics was call it 100 million class mission. Everything, the science, the launch, $100 million. Not billions, right? So one tension was how do we satisfy the NASA, system engineering way of life while trying to be a lean, mean, cost-capped, competitive Earth venture mission. Right? So there's a lot of lessons in that tension of operating lean. However, and we need to be reliable, and we need to document what we're doing. Maybe not to the extent of a James Webb. But there's some happy medium in there that we thought that we tuned into. Right? So there's that kind of story. There's the mission assurance stuff. Another big takeaway. I don't think there's anything super profound, but this is a pretty complicated mission, Tropics. There's a lot going on there. So the requirements, doing a really good job at the outset of articulating the requirements and sticking to those early, right? So we don't want mission creep. We want good enough. We want to know what good enough is. We don't know what the relief valves are, right? descopes. So it's that kind of stuff.
Let's see, do we have any questions online? We do not.
Okay. Yes.
I have a question. Thank you very much for this very exciting presentation, and congratulations on the successful mission, and good luck on the upcoming missions. And so what you said that the data from ATMS, I believe it was called, and then also your tropics data is most powerful in terms of predicting cyclone path. Why do you think that is, or do you have an idea? Do you know why that is most predictive?
So for the case of tropical cyclone path, so the hypothesis on a lot of that is to what extent does the environmental conditions drive the storm? If there's moisture around the storm, how can I leverage that to help me understand what it's going to do next? Okay, for example, that. So environmental moisture. Another thing is things like the structure of the storm, the asymmetries, the width of the rain bands. How does that impact intensification? We can measure both of those with tropics, and the answer to that, so those markers do help us understand that they are correlated with intensification. So we're using those drivers with this improved revisit to help us. That's kind of the conjecture. I don't think we've definitively shown that that's why. But those kind of, we have, kind of circumstantial evidence that it's something like that, we are doing a better job with the environment to constrain what the forecast is doing. And, the way we look at that, so we can ask the forecast model, okay, give us your sense of the atmospheric conditions. The moisture is a function of altitude around the storm, and with tropics and without tropics, and which one is more physical to the extent that we expect things. We can kind of, calibrate the model out to that way too. And so we have more physical results with tropics, which is comforting. So it's that kind of stuff.
Okay.
Yes.
How does the eye determine the direction of the storm?
Yeah, so I don't think the eye itself determines the direction of the storm. The eye is more of an intensity indicator. Yeah, the direction. There's all kinds of stuff. So it's like wind shear and asymmetries and all that. That's more in tune to the direction of the storm. But the eye properties is more intensity. I'm not a meteorologist, but that's my understanding.
I bet you know more than us.
I don't know. It's close. Yes.
We've got a question online, which is any comments on IR or a sun shield?
Okay. So the infrared measurements are extremely useful too, and as evidence of that, so the Europeans, before the US, by the way, this kind of hurts, but the Europeans just launched last year a geostationary infrared hyperspectral sound for the first time. Okay, a lot of people are excited about that. We're still waiting to see the data, but that should be kind of an acid test of how good the infrared can be for storm. And that one, again, the infrared is classically limited by the cloud tops, but the environment around the storm, when we're talking about that's important, they can do a great job with that. So I think the infrared is super important. And the microwave's not going to put the infrared out of business. We'll see. We'll see that with the infrared hyperspectral coming on geo. That's a big deal. Now there's something about a sun shield.
Something about a sun shield.
Yeah. So my guess is, why not use a sun shield to lower the degree of difficulty on the cruiser thermal design? If that's the question, I made that question up on the fly, but if that's the question, that's a good question. Because I think that the biggest challenge with cruiser is having a reflector array, out in the sun, going through, the eclipse, and then you're in the sun, you're out of the sun, you're getting 200 Celsius swings. The panel's lossy, so you have to calibrate that out. It impacts your sensitivity. How do you deal with that? So a sun shield would help with all that, if we could do that, if that's the question.
Oh, they say yes.
Okay, oh, great. Yes, awesome.
I think we are just out of time. Maybe.
Marty.
I think we have exactly 1 minute left.
Oh, okay.
The phased array, so this is all passive, it's not radar.
That's right.
And the phased array, it's reflective to a point?
Yes.
Oh, okay.
Yes, that's right. The
So-
feeds,
so-
it's focused at the feeds.
So it's not like all the array elements are signals that there are added up and piped out somewhere. You reflect the signals down to a central sensor.
That's right.
Okay,
Yeah,
and
so
and then you have to refocus the array for each band.
Exactly.
Okay,
Yep.
all right.
So each RIFIC in there has 6 channels on it. 4 for the 50 to 58, 1 for the 24, 1 for the 30. So each one of those independently, each of those 6 is moving their beam around where it needs to go.
Oh,
At each location.
so each little antenna element, there's actually 6 different tuned
Correct.
elements in each.
That's
Pixel.
correct. Yep. So each of these things are like 5 millimeters across a unit cell. They have 6 radiating elements in there. There are 4 patches and 2 linear array, two linear patches.
Okay, do we make it?
Thumbs up. I think we're good. Let's give it up for our speaker one more time.
How long will they stay in orbit and be functional?
They just came down last year. So as planned. So our requirement was 1 year of science. We got almost 3, so we overperformed by a factor of 3. And they came down. The solar maximum didn't help us with that, right? They came down a lot really fast with the solar maximum.
And stay tuned for upcoming events. We've got plenty of outreach happening. We've got State Street Science Fair coming up. And possibly some networking mixers. Yes, I know.
Keep your eyes
Those ones are
out.
always popular.
Every time my previous PI, if I'll volunteer to remind someone, I would love to get them.
Well, cool.
I said a lot earlier, so I just grabbed the
Thank you guys. I'm gonna put it up for
Yes, yeah, Ariana and,
Yeah.